Thank you, James, Mark, and Miles. They are going to be discussing today Snowflake and Dask, how to scale workloads using distributed fetch capabilities. I'll let you guys introduce yourselves. So please go ahead.
Hey, everybody. Thank you for joining today. This session is titled Snowflake for Dask. And we'll have three of us on here today to kick us off here. My name is Miles Adkins. I'm a partner sales engineer here at Snowflake, and I cover our AI and ML ecosystem from the partner perspective. James?
Yeah, hi everyone. My name is James Bourbeau. I'm a Dask maintainer and also the lead open source engineer at Coil, where we work on things like Dask and other projects in the PyData space.
And hi, my name is Mark. I work at Snowflake as a software engineer. I mostly work on our open source Python projects, such as SQL Alchemy and our Python connector.
Great, thank you for that, Mark. So just to kick us off here, just to set some context, I know Snowflake has gained a lot of popularity over the last several years. Just wanted to give you an intro to kind of what is Snowflake and what differentiates us from a lot of the other cloud data warehouses out there. And so Snowflake is really a scalable data platform as a service, whereas a lot of the other cloud technologies in the data warehouse space were really just on-premise technologies that were kind of lifted and shifted to the cloud. Snowflake was architected on the cloud. So what that means is we were able to take scalable services like S3 and EC2 and really architect and build off of those technologies as opposed to just bringing up Postgres to the cloud. And what makes us unique here is really our 3-layer approach. At the bottom layer, we have our kind of centralized storage. We really believe in this idea of you should have just one copy of the data, and if you want to share that data somewhere, you just initialize and govern a share as opposed to making another copy of that data, doing some sort of FTP process, or just emailing your data, and then going on from there. We find that often that those pain points cause a lot of disruption, time, and value loss to a company. And so, we wanted to keep all the data in one place. The second layer here is our compute layer, which is completely isolated from storage. So storage and compute, you can kind of scale up to your desired levels there. And you can think of this as, if you deploy on Google Cloud, they have their own compute service. If you deploy on AWS, we have EC2, and same for Azure. This allows you to scale all of your workloads both up and out as you need to. Up meaning, I have more and more and more data that I'm starting to work with in my data platform. You can get and request a bigger and bigger instance size. And then out meaning, hey, I'm onboarding a new set of users, or I've let a new group in my organization get access to Snowflake, and I'm starting to see my number of queries per second, continue to rise. We give you the ability to spin up more and more and more servers in a kind of a multi-cluster compute fashion to service kind of the needs of your users as well. And then the last layer here, this is really kind of what we call the brain of Snowflake, is our cloud services layer. This is where we handle all the stuff like security and governance, our sharing and collaboration features, query optimization, and then of course also kind of that SaaS layer as well. So this is kind of how we deliver Snowflake to you as a service, where you really only pay for what you consume. You don't have to spin it up, let it run idle for a while. It's really a quasi-serverless experience for you. And so what this enables, this data cloud platform, is the ability to ingest really all 3 types of data: structured, semi-structured, and unstructured data as well. enabling 6 distinct workloads all on one platform. Whether you're doing data engineering, you have different types of data science applications, or you're just building, more general data applications. All of those can be powered by Snowflake. And then, of course, being able to reach a variety of different types of data consumers. Now, to go a little bit deeper here, we know that Snowflake is still not going to be able to cover the entirety of kind of the mass amount of data workloads out there. What we've kind of engineered is a bunch of a big ecosystem of connectors, whether it's our Python connector, which we're going to go into in a little bit here, JDBC connector, ODBC connector, for you to really be able to hook into the Snowflake platform. Now, for a while, the only way to really move data across from one app to another was through a single pipe. And so there was no way to really do any sort of parallel data movement between Snowflake and your application. And so with that, I'm happy to pass it over to Mark, who's going to walk through our latest innovation, where you can now really grab your result sets and read and work with those in parallel. Mark.
Thanks, Miles. Could you please go to the next slide? So I would like you all to imagine dealing with a terabyte of data. It's hard because it's impossible to hold it in memory all at once, unless you have some sort of super expensive machine, that is. For this reason, when a SQL query in Snowflake returns a large amount of results, it gets broken into smaller pieces. We call these result chunks. Each of them are a few megabytes in size, and they can differ from one another. The sizes. Then the different connectors will fetch and convert these for the users to the respective language-specific objects. But as you can imagine, synchronously processing a terabyte of data will still take quite a long time, even with optimal code. So the only way to scale past a certain point in Python is to distribute the work between multiple processes or machines. However, this was impossible with our old monolithic design of the result fetching mechanism. Because information that was vital to processing was discarded as soon as it was consumed. Miles, can you go to the next slide, please? So this is where the idea of result batches was born. They represent the result chunks generated from Snowflake in a one-to-one fashion on the connector's side. We set out with a few simple goals in mind. Primarily, the result batches had to be standalone. This would allow them to be consumed independently without their own connection to Snowflake. To allow for easy distribution between processes, these result batches had to be serializable. To keep them standalone, this meant that we would need to serialize some of their metadata in addition. But we were careful because we didn't want to lock users into a particular parallelization method. For example, if we were to enforce multiprocessing onto the whole Python connector, then it would just not work in AWS Lambda. To complement our existing ability to convert results into pandas data frames, we wanted to allow converting to arrow tables as well. This was a much requested feature by our users. Finally, but still very importantly, we didn't want to break or regress performance of pre-existing use cases for non-distributed result fetching. These still needed to have some sort of pre-processing logic. So to kind of bring it all back together, in a nutshell, the final design has all of the result functionality pushed down from the overarching result set level to the individual result batch level. as an example, instead of iterating over the entire result set, we iterate through each of the result batches individually. Nevertheless, we need to support our existing use cases. To accomplish this, we created a result set class. It composes multiple result batches together using a simple iterator logic and interface. This class also supports prefetching chunks for consumption later, and it uses simple multithreading. This result set class also serves as an example of how we envision our partners to implement their own concurrency strategies. I would encourage partners to use it as a starting point for their own designs. We also made sure that result batches are lightweight, replayable, and most importantly, serializable. This is to make sure that they can be distributed to other machines easily. We also added some extra metadata information to each of the result batches, like their size. And this was to allow people for more intelligent distribution between processes. For me, the coolest part of this project was to see all of the new use cases that it enables for our users. Internally, we had one of these presentations where one of our sales engineers presented a way of performing deep learning on all of these individual result batches. And then once he had all of the resulting models, he was then able to merge them back together at the end. And this enabled him not only to push his computer as hard as he could if he wanted to, but it also gave him the option to just have it running in the background and maybe, allow him to run another process in the foreground without taking over his computer. I had no clue that something like this was even possible before. So for this reason, I would like to ask you to reach out to me and let me know how distributed result fetching enabled you to do something new. And with that, I would give it over to James.
Yeah, thanks, Mark. I'm going to see if I can share my screen. Share desktop 1. Hopefully you see some slides right now.
Yep.
Let me go ahead and put that into present mode. Can you still see the slides, or are you seeing presenter notes and things like that?
You'll see your slides here.
Awesome, great. Thanks, Miles. Thanks, Mark. So yeah, so I'm going to the second half of this talk is about integrating this new distributed fetch capability from Snowflake with Dask. So to kind of summarize so far on the Snowflake side, so Snowflake is a centralized data storage service that has a highly optimized SQL engine. So really good at storing, serving data, and again, this sort of incredible, highly optimized SQL engine. However, Snowflake itself is sort of a data access system, which could, and management system, which could benefit from more advanced operations in Python. Like for instance, machine learning or any other kind of advanced analytics you might be used to in the PyData space. So how do we go about sort of connecting Snowflake as a system to Python? So for instance, there are a couple of kind of ways in which you can connect the two. The first is on the data ingestion side. So you may have some, complex data sets that you're working with. Maybe you have some simulation data like being displayed here, or some weather data that you need to, sort of massage and process into a nice form that you can then store into Snowflake. Another option would be on the output side. You may have some existing data in Snowflake that you want to run a bunch of machine learning models on. You want to, sort of apply a trained XGBoost model to an entire table in Snowflake. This is a really common thing we see at financial institutions, for example. Dask is great at these sort of scalable PyData solutions. So a couple things to know about Dask is that it is okay at SQL-like operations. So this is really, I mean, Dask can do SQL-like operations and support some, but it's not really a place where it shines. That's more a place where Snowflake shines. Dask itself also is not, it's not an integrated storage. Dask itself isn't a storage system. It's a compute system. So Dask does not, Dask can, talk to storage systems like Snowflake, but it itself is more of a compute engine. Places where Dask does shine are that it's great for sort of advanced analysis and machine learning. It's also really good at handling non-traditional data. So it can handle tabular data, for example, sort of the more SQL-friendly type data sets. Dask can handle those. There's Dask Data Frame, which is sort of a parallel version of Pandas that handles tabular data incredibly well. Dask also supports not so SQL-friendly data sets. So again, going back to sort of these complex, maybe ND array type data sets that you might be using projects like Xarray for instance. Dask supports those types of data sets as well. So this is sort of a summary of the last couple slides. The take-home message is Snowflake is really good at data storage and SQL performance. Dask does not shine in those areas, but it does shine in the machine learning space, the advanced analytics, and not working with non-traditional data. So both of these sort of technologies are sort of excel in certain spaces, and we can bring them together to kind of get the best of all worlds. We can get the best of data storage and SQL performance, and the best of machine learning and non-traditional data analysis by combining the two. So now we move to the technical question of sort of how do we combine these two technologies? There are a variety of ways in which you can combine Snowflake and Dask, and I'll sort of walk through all these options that sort of have been used in the past. And at the end, I'm going to spend some time and highlight this new native parallel reading technology. So sort of integrating the stuff Mark talked about, this distributed fetch, into Dask. So the first option is to not use Dask. This is always a great rule of thumb. Don't use Dask if you don't have to. If your data sets are small, which many are, just use Snowflake directly. Snowflake has a Python connector that you can use to execute queries and fetch, Pandas data frames from Snowflake. This is already available. It's super simple to use. That's sort of the pro. The con is it doesn't scale well. So if your data sets are as Mark mentioned, a terabyte large in size and sort of larger than your local machine's memory. The local memory on your machine, you can't fit it on your laptop, say, doesn't scale to those situations. The next option is to use Dask's read SQL table functionality. So this is great in that it allows you to start using Dask, which allows you to have distributed and larger than memory read and writes. It uses SQL Alchemy under the hood, so it can actually talk to Snowflake, but lots of other database technologies as well. So it works on all major databases. So what happens under the hood here is you can imagine having like a giant table of time series data. You can imagine taking sort of the querying to get the minimum and maximum and sort of get a sense for the expected size of the data, the minimum, maximum in time, and then split up that data set, the time series data set, into a bunch of smaller sort of uniformly sampled queries, and then executing each of those queries for each partition of this data set in parallel. That's sort of under the hood what read SQL table does. This work was led by a handful of engineers, led by Martin Durant at Anaconda. This works, but it does have some cons. It's slow because it's backed by ODBC. It also doesn't support complex queries. You can imagine if you had two tables that you want to join together and then query that result and maybe do some other operations. Sort of the actual final table you're interested in, it can be hard to determine what subqueries, sort of construct the subqueries to sample that table in parallel. You also have the risk of inconsistent results. If you are making a query on a table that someone else is writing to at the same time, you can imagine how you can get inconsistent results. The next option is using Dask's delayed interface. So the good folks at Saturn Cloud have put out some documentation around how to go about this approach as well. This is great in that it supports reads and writes, and it's actually relatively straightforward to read. You're just writing some load function, which you run in parallel. This is sort of doing a more explicit version of what's going on inside Dask's read SQL table. Again, it has a similar sort of downsides to this approach. That it's backed by ODBC, so it can be slow. It doesn't support complex queries, and it also get the risk of inconsistent results. It does require some manual sort of effort, so you have to build up all of these subqueries manually, which often requires some knowledge of the underlying data set that you're trying to query. But this is really great for educational purposes. I think it's really explicit and clear as to what actually is happening under the hood. The next option is to take your data set and just export it to some, file dump. Basically, you can take your query and get their query result and dump it to a bunch of CSV files, or dump it to a bunch of Parquet files in S3. You can then use Dask and other technologies to use these standard file formats. Read in, say, a data set of Parquet files on S3. This is really fast, both at reading and writing, because all these technologies have focused on, for instance, formats like Parquet and the I/O with those file formats. The downsides here is that you're sort of copying your data sets. So this can lead to data bloat in your storage systems. You also now have sort of multiple copies of your data floating around. It's hard to tell where the source of truth is. You no longer have a single source of truth. And in general, your database admins will just be sad whenever you are sort of replicating your nice database into a dump of Parquet files. But this is a valid option. So yeah, sorry, I forgot there's a code sample here to show you how to copy in a data set from a Snowflake table into an S3 dump Parquet files. So this is sort of some of the existing ways in which you might have in which Dask and Snowflake have been integrated in the past. So today we are excited that there is a new path forward with this distributed fetch capabilities that Mark talked about. So today there is a Dask Snowflake package you can install. You can pip conda install Dask Snowflake and have Snowflake use under the hood. This utilizes Snowflake's new result batch technology. So we can have fast parallel reads. It will auto partition, and it does support complex queries as well. And because Snowflake is managing this data, we're not like, say, dumping to a bunch of Parquet files. Snowflake is able to do all the things it's great at. It's able to handle automatic cleanup and lifecycle management of your data sets. So I want to move on to a demonstration real quick here, which highlights Dask Snowflake in usage. So here, spinning up a Dask cluster. This happens to be using Coiled, but this could be any Dask cluster. Moving on a little bit. Here, we are we're sort of setting up this large query here to execute on some data set in Snowflake. So notice this isn't a, from table select all. This is a complex query. This is like a big system here. We can then use Dask's read Snowflake function here, which takes in a query and actually returns a Dask data frame. So here, we're executing this query. We're sending this query off to Snowflake. And we can see starting to appear in the Snowflake's UI, the query has made its way to Snowflake. This is, again, this larger complex query that we'd like to have happen. Snowflake then, sort of does its thing, and we can see all the Snowflake, the execution, the SQL execution optimizations happening all inside Snowflake. And what we get back is a Dask data frame. So we get back something that we can now sort of hand off to the PyData stack to start doing all of the normal PyData operations we're used to doing. So for example, we can, so here we can see things appearing in the Dask dashboard now. We can do things like train an XGBoost model. So here we're setting up our XGBoost model, and we're starting to train it on all of this data that we're getting from Snowflake. So that's sort of how we can use Dask and Snowflake right alongside each other. Looking under the hood a little bit, so what happens is you have your Dask client sitting here. I hope you can see my mouse. I'm moving it around the Dask client. So what Dask will do is we'll send that SQL query to Snowflake. Snowflake will then send back metadata for all of the individual chunks in your Dask data frame. So Dask will then take that metadata for each of those result queries and send those off to workers in your cluster. Those workers are then able to each independently talk to Snowflake and have the results for each of these chunks sent back from Snowflake efficiently using PyArrow. Because Snowflake is managing all of this data access here, it's able to clean up automatically and all is right in the world. So just to sort of summarize things real quickly. So Snowflake is a fast and easy SQL data warehousing service. It's great at, as we've said, sort of data storage, SQL queries, and Dask is a general purpose distributed computing framework. We've now, engineers at Dask and Snowflake have built a bridge between these two technologies, allowing users to really have the best of both worlds here. If you're interested in trying this out, you can pip install Dask Snowflake or go to the Dask Snowflake repository there to get more information from the documentation. If you have any more questions about Dask, feel free to join Dask's community Slack channel. We're linking to the invite there in the slides. And with that, I'll maybe bring Miles and Mark back if you have any questions or to answer questions from users or from attendees.
So thanks, James, Miles, and Mark. We have one question in the Q&A here. How does this compare to Snowflake plus Spark, both from a support and performance perspective?
Miles, Mark, I'm not sure if you want to take this, or if I'm also happy to.
Yeah, sorry, I was just unmuting. So actually, our Spark connector works very similarly to what we exposed. And so kind of the Python work is, it's loosely based on what Spark does. And the performance, we can talk about Python versus Java, right? Or I'm sorry, it might be Scala, but like those sort of constraints still stand. But we did everything we could to make this as performant on Python as possible. So I say it's comparable. And you guys obviously know what that means for Python.
Yeah, and maybe just to follow up on the support side of the question, depending if you're managing your own Spark cluster or if you're going with a managed service like Databricks, there's obviously kind of implied cost for that. Snowflake is 100% self-managed. You don't have to worry about what server size I'm going to choose, et cetera. And then for Dask, it's really a much lighter weight, framework that you can also bring to your kind of infrastructure of choice. And we've really optimized the connection between the two using the Arrow format. Now, there's nothing stopping you from bringing Spark into that equation as well if you wanted to. But in general, what we've seen is from a support perspective, Dask is super easy to manage. Snowflake is managed for you. And so there's not all that overhead of managing these Spark clusters, which you don't know how to size exactly. And those costs can run away from you.
Great, guys, we're out of time now. So if there are any more questions for Miles, James, or Mark, please ask them in Slack. So thanks again, guys. And I'm going to stop the recording.